Hi, everyone, and welcome to our first CARSS webinar. My name is Sahar, and I'm the Center Director at CARSS, short for Center for Autonomic Recording and Stimulation Systems. And I'm in charge of operations and technology integrations of our multi-component neuromodulation system. So the generous funding source that has awarded the CARSS Center is a sub-program within the NIH Spark initiative that aims to accelerate development of bioelectronic medicine. And the problem that's been identified within this initiative is that current clinical grade neuromodulation platforms are costly to develop from ground up or just difficult to access for exploratory use. So our goal here is to advance the clinical translation of bioelectronic therapies by developing open source system for use in first-in-human trials so that interested parties can either make the exact parts of the design or make modifications based on their end user needs. The team working to develop each components of our technology consists of 3 USC investigators and 2 industry partners. Doctors Alice Meng, Maral Musavi, and Hengbo Zhao from USC are developing novel cuff electrodes and sensors. Dr. Victor Pickhoff from MediPace and Mr. Raja Hitti from MedAlly are developing more established neuromodulation components with the strategic goal of speeding up development and FDA regulatory approval process. The technology integration and dissemination and admin core team consists of 3 USC staff who are all actually USC alumni. So that's me. Dr. Alex Baldwin is our research associate, and Pallavi Gunalam is our project admin. So at a high level, the CARSS system consists of multiple components that are all integrated to create a closed loop or open loop neuromodulation system, where it receives signals from end organs, processes the signals, and provides feedback on how to modulate the nerve to get a desired effect by sending stimulation pulses to design electrodes on the autonomic nervous system. The stimulation electrodes we're developing are all extraneural. So the image in the middle here demonstrates the possible locations of cuff electrode placement on the vagus nerve. MedAlly is developing a PDMS cuff for cervical nerve trunk, which, as you might know, there are a couple of vagus nerve cuff electrodes with FDA clearance in the market. The issue with stimulating the main branch is that it supplies many organs, and therefore it might cause undesirable side effects. So we're also designing thin film parylene cuff electrodes with diameter of less than 1 millimeter for small branch fibers to increase selectivity. Sacral nerve is another autonomic nerve that controls the bladder and rectal muscle, and its stimulation is used to treat patients with bladder and fecal incontinence. So our industry partner, MedAlly, is designing electrodes to interface with this nerve as well. For a closed loop mode, we're developing physical and chemical sensing at USC. The chemical sensors include catecholamine and acetylcholine sensors. And just as an example, down or up regulation of these chemicals has shown to provide feedback on the functional or disease state of an organ, which can then be used to provide an alert to the patient or clinician. We also have a pH sensor, which may be used as a biomarker for disease, for example, in detection of stomach acid, urinary tract infection, and so on. Our physical sensors include temperature sensing to monitor inflammation and strain sensors to detect changes in static movements such as bladder fullness and bowel stretching. So keep in mind that these indications discussed here are all examples, and the actual clinical indications will have to be defined by the user. In addition, we have an assortment of more established and end organ sensors, such as motion sensor and EMG to monitor dynamic activity, and ECG to detect heart rate variability for extraction of sympathetic and parasympathetic activity. These electrodes can, of course, also be used for stimulation. Lastly, the implantable pulse generator, or the IPG, will be the brain of our system with capability to analyze signals from all of these sensors, generate electrical stimulation pulses, and communicate with an external component such as phone or tablet. This unit will also include all of the mechanical components such as universal connector and packaging of the hardware. So in summary, the projects are divided into 5 components, which we call nests. Nest 1 is led by MedAlly to develop the mechanical components such as enclosure, a header with connectors, and Bluetooth antenna, a charger designed to allow wireless power transfer, and commercial phone and tablet for patient clinician remote control. Nest 2 is the electrical. So it includes circuit board design for pulse generation, sensing, power management, and Bluetooth communication, along with code to control the hardware. This is all led by Dr. Victor Pekov's team. Nest 3 is the development of an assortment of more established electrodes and leads, ECG, EMG, and motion sensors. These are all developed by MedAlly. Nest 4 is led by our USC PI, Dr. Ellis Ming's team, working to develop a novel polymer-based cuff electrode for stimulation of branch fibers with a cuff diameter of less than 1 millimeter. And Nest 5 is led by our USC investigator, Dr. Hengbo Zhao's team, working to develop mechanical and temperature sensors, and Dr. Maral Moussavi's team developing pH, acetylcholine, and catecholamine. Thank you for your attention. This was a very high-level overview of our system. You will then hear from each lead developing individual elements of our system, followed by an approach to disseminate open source content to the neuromodulation technology.
Hello, I'm Jamie Coates from MedAlly. I'll be sharing Nest 1 and Nest 3. So first of all, MedAlly was established in February of 2011 with a focus on active implantable medical device development from design through production. Located on the outskirts of Charleston, we are an ISO 13485 certified company. We have 10,000 square feet of production with 3,000 square feet of clean room. Our capabilities include laser welding, hermetic welding, robotics, braiding, molding, and more. And we also provide full design and development services. In Nest 1, we're focusing on the mechanical enclosure of the IPG along with the charger. And in Nest 3, we're focusing on a number of leads to support that system. For Nest 1, we're implementing technologies that will enclose the electronics that Victor in Nest 2 is developing. We are developing mechanical closure that will support the modular approach that the team is implementing to enable many different uses of the device. To minimize risks for the users, we will use proven technologies in the development of our IPG. The designs have been optimized for this modularity. Specifically, the IPG will have the following features: our hermetic enclosure for the electronics portion that supports housing all the sensing and stimulation control, as well as housing the charging electronics and the rechargeable battery. In the header portion of the IPG will be a Bluetooth antenna and 4 independent lead boards with 4 connectors each. A 2-lead configuration with 8 connectors is also being developed. The hermetic enclosure will be made primarily of titanium that will be laser welded together to form the hermetic barrier. The titanium grade selected for the enclosure is selected to facilitate the charging without overheating the IPG during charging once implanted. The titanium case can also be marked with any pertinent labeling and identification that is desired or required by regulatory authorities. As for interfacing with the IPG, the header has 4 lead access points with 4 ball seal IS4 style contacts, or, like I said earlier, 2 8-contact leads. Additionally, there are 4 sets of set screws to secure the leads into the header. Additionally, Nest 1 includes the external charger that accompanies the IPG. Accompanying Nest 1, we are also developing materials for Nest 3. Nest 3 incorporates a series of standard leads to enable new research. Included in this list is an SNS, or sacral nerve stimulation lead style with 4 contacts, a cuff lead with bipolar electrodes, an EMG sensing lead, an ECG sensing lead, and an accelerometer-based motion sensing lead. All leads are to support the modular design and to allow for simple integration for each one. The lengths of each of these leads can be varied as needed. And additionally, there is an interconnect that will allow from a 4-contact lead that connects to the header to split into 2 independent bipolar leads, allowing for even more versatility. Thank you for your time today, and feel free to contact me at any time if you have any questions.
Welcome to Nest 2. I am Victor Pikov from Medipace Inc. And in Nest 2, we are planning to develop PCBA and firmware. PCBA stands for Printed Circuit Board Assembly. And the firmware is the basically software running on that PCBA. We are planning to use several concepts in order to make this an effective technology. So first, we are planning to use low power, low noise, and small size. And in order to do that, we have selected the chips, as you can see on my left, which have several low power modes, including some that are below 1 microamp and also use automatic voltage regulation. Also, we are planning to use full fail-safe operation of the PCBA for long-term reliability. To do that, many circuits have redundant components and redundant ways of controlling them, and also methods for assessing their proper function. Another concept we are incorporating is modularity. As you can see on the right, the stimulation circuits are in the red area, and multiple sensing circuits are in separate green areas. Depending on the stimulation target and disease indication, the stimulation channels can be adjusted from 1 to 8, and the sensing channels can be selected based on the use of EKG, EMG, temperature, and other sensing leads. Another concept we're incorporating is the use of commercial off-the-shelf components. This is done for future-proofing the design, for reducing the design costs, and for getting advantage of latest circuits in consumer electronics, such as our cell phones. And finally, we plan to use simple and proven rather than complex and high-risk technology. We will use advanced Bluetooth technology for communication, as it's already been shown to be effective in other FDA-approved implantable devices and is a mature technology. But for other circuits, we will use even more reliable, older technology that's been tested for decades in other IPGs. We are presently in the process of fabricating the first PCBA prototypes and plan to complete this testing later this year. We will also plan to finish developing the first firmware version by early 2024, and we'll test the whole IPG with all the electronics in a chronic pig study later in 2024. We are in parallel also developing a charger and an Android app for controlling the IPG that will also be finished in 2024. So in a nutshell, this is Nest 2, and thank you for your attention.
Hello, everyone. This portion of the webinar is on Nest 4, which is the microfabricated cuff electrode for interfacing with smaller nerve fibers. My name is Brianna Thielen, and I am a PhD student in the Biomedical Microsystems Lab at the University of Southern California, and I'm working on this nest with Dr. Quentin Rezard under the advisement of one of our project PIs, Dr. Ellis Meng. The motivation for this nest is the current lack of options for interfacing with nerves less than or equal to 1 millimeter in diameter. Existing clinical cuff electrodes are built from bulk metal or metal foil embedded in thick PDMS, which is difficult to scale down to a sub-millimeter size. Additionally, stiffer bulk metals don't interface well with small, delicate nerves due to their difference in mechanical properties. To fill this technology void, we are developing a polymer-based helical cuff electrode for nerves less than or equal to 1 millimeter in diameter. A mock-up of the microfabricated cuff is shown in the image on the right, with the polymer backbone in white and metal electrodes and traces in gray, wrapped around a pink nerve. The device will be microfabricated from thin film polymer and thin film metal, and will be both soft closing and self-sizing. We will also build a surgical tool to allow for endoscopic placement of the cuff on deeper nerve branches. The cuff electrode will be made of perylene C as the backbone and insulation material, and platinum as the conductive electrode material, with either perylene or PDMS insulation between electrodes to contain the electric field during stimulation. All of these materials are compatible with standard microfabrication techniques and are commonly used in medical implants. The image on the left shows a cross-section of the thin film layers in the device, illustrating the approximate geometry. Two perylene layers sandwich a patterned platinum layer, with openings etched in the top perylene layer to expose only the electrode sites for stimulation, leaving the traces fully insulated with perylene. The image on the right shows a fully fabricated device with two helical cuff electrodes connected to a perylene cable, which makes a U-turn above the device. Two metal traces are embedded in the cable, one connected to each electrode. At the end of the cable, the traces will be connected to the med ally leads, which are used across all nests for connection to the IPG. Due to the flexible thin film construction of the device, the electrode cuffs can be easily opened with the surgical tool, but maintain memory of their original shape, enabling the self-sizing property. The U-turn cable acts as a service loop to prevent device movement during the implantation and anchoring procedure, as well as during any motion in the body after implant. The cuff electrode will come in two sizes, both of which will be self-sizing within their given ranges. The small cuff will fit nerves between 0.5 and 0.8 millimeters in diameter, with a 3 millimeter spacing between electrodes, and the large cuff will fit nerves between 0.7 and 1.0 millimeters in diameter, with a 4 millimeter electrode spacing. The platinum electrodes will be sized to allow safe stimulation up to typical maximum parameters for vagus nerve stimulation, with the option of electroplating or coating the electrodes if a larger charge injection capacity is needed. We are also planning a battery of tests to determine other mechanical and electrochemical properties which may be relevant for different research applications, along with accelerated soak testing to monitor these properties over time. We are currently in the process of testing multiple cuff geometries for optimal handling and surgical placement, and plan to have completed the first design by the end of next month, after which we will fabricate prototypes for preliminary testing. By the end of 2023, we will have complete designs of the surgical tool as well as test procedures for the cuff. Throughout 2024, we will be releasing benchtop testing reports and other design documentation, and by mid-2025, we will have completed the evaluation of the cuff both on the benchtop and in a small animal model, and will release all documentation of the cuff and placement tool. Thank you for your attention, and please direct any questions to the chat.
Hello everyone, welcome to this webinar. My name is Xing Hao. I'm a PhD student from the Nest 5 working with Professor Hanbo Zhao and Dr. Xiangling Li. Our team's mission is to build temperature sensor and strain sensor to provide feedback for the neuromodulations. The reason we need these two sensors is that temperature and motility at an organ can provide valuable information about the organ's functional states and detect disease symptoms. Many diseases such as infection and inflammation can lead to temperature change. For strain sensing, our organs such as bladder and intestines can have large expansion and contraction. Measuring their strains can give us information like volume changes, which are related to activities such as urine accumulation or food digestion. To measure temperature, we propose a thin film temperature sensor that uses platinum metal. The reason is that resistance of metal can change linearly with temperature, and the rate is defined as the temperature resistance coefficient. We designed both 10 micron and 20 micron platinum lines, which are patterned in zigzag structure using lithography and lift-off process. The sensor's area is about 1 by 1 centimeter, and the active sensing area is about 5 by 5 millimeter, as you can see from the bottom. We expect the baseline resistance to be about 33 kiloohms and 133 kiloohms, 130 kiloohms respectively. Such large resistance is able to overcome the effect from the lead resistance. The platinum layer was positioned between two layers of polyimide, and we also left several holes at the boundary of the sensor for suturing purposes. To test our fabricated temperature sensors, we placed them on a hot plate and varied the temperature from 30 to 45 Celsius, which is a common range in body temperature. The temperature was measured by an IR camera, and the resistance was measured by an LCR meter simultaneously. We can see all sensors have similar temperature coefficient of resistance during temperature rise and drop, and the trends are very linear. We found the resistance change is about 4% during this 15 Celsius temperature change. Since the least significant voltage level in our current IPG's ADC is about 0.37 microvolt, our temperature sensor can measure at least 0.04 Celsius temperature change, which is sufficient for our applications. To measure the strain at an organ, we decided to use stretchable capacitive strain sensor with the standard parallel plate design. As you can see in the first figure, when the sensor is stretched, the overlapping area between the two conductive electrodes will increase, and the thickness between them will decrease. Thus, the total capacitance between the two electrode layers will increase with the increasing strain. Our strain sensor can stretch up to 100% strain and maintain good stability. From the tensile testing results shown at the bottom, we measure it has very low hysteresis, and the capacitance reading did not drift significantly during the load and unloading process. To make a stretchable encapsulation layer, we decided to use Parylene first, since it's biocompatible and it has good hermeticity. We first pre-stretched the sensor and deposited Parylene C on its surface. Upon releasing the sensor, the contraction will spontaneously create wrinkled Parylene structures, as you can see at the right-hand side. Since the wrinkle structure can allow the sensor to maintain a constant width during stretching process, it actually increased the sensor's gauge factor from 1 to 2.1, which made our strain sensors even more sensitive to strain. We also started building a benchtop test setup and phantom organ to test our sensors. Here on the left, you can see a linear stage system that can push a large syringe to inject water into a phantom bladder, which is made of EcoFlex silicone. We wrap the strain sensor around the bladder with some silicone adhesives. When the bladder expands and contracts, the capacitive strain sensor can clearly measure the surface strain induced by the volume change. From the data shown at the right corner, the capacitance can also return to the initial value right after the bladder returned to the initial state. So that's our current progress. We still have many things to work on. First, we need to test both temperature and strain sensor in PBS solution and also attach them on phantom organs during even larger deformation. To improve the long-term sensor functionality and verify suitable encapsulation materials, we'll prepare measurement devices such as interdigitated finger electrodes to test different encapsulation materials. Some options we have in mind are PDMS and some commercial product like Alkan silicon. The interdigitated electrodes will measure encapsulation materials impedance and indicate if water penetrates the encapsulation layer. Lastly, we'll finish up the benchtop test setup, completing all functions, and as you can see in this illustration, we will use a large glass tank with solution to hold liquid, and use a heater to control the temperature. We will immerse the organ with sensors in this temperature-controlled liquid environment, and then test both encapsulated sensors in the thermally accelerated aging method to make sure both sensors can have long-term functionality. Thank you very much, and thank you for joining this webinar.
Hi, everyone. I'm excited to be sharing the second part of NEST 5 and in continuation of the other NEST in the center project. In NEST 5, we're developing electrochemical sensors for measurement of pH, catecholamines, and acetylcholine. I'm Maral Musavi. I'm co-I in this center project, leading the development of electrochemical sensors. We're interested in monitoring the levels of these biomarkers, specifically neurotransmitters, because of their importance in signaling. We can get information about the state of organs through monitoring the levels of these neurotransmitters. Specifically, we could use this information for closed-loop neuromodulation. For example, pH will provide critical information about the state of organ, and in any sort of disease versus functional state, there will be major changes in pH levels in the tissue. What we're developing is two separate modules that could also be combined together, where you are able to pick either the catecholamine module or the acetylcholine and pH sensing modules. These are electrochemical sensors that can be implanted in vivo continuously for monitoring the levels and to provide feedback for closed-loop neuromodulation. We use two different mechanisms of sensing. We utilize electrochemical sensing, specifically oxidation of catecholamines, to enable antibody-free recognition and selective detection of these molecules. For acetylcholine and pH, we use a different sensing mechanism. The fabrication of these sensors utilizes perylene C as a flexible material and platinum electrodes as conductive leads. These are thin, flexible sensors that will cause minimal scarring of tissue and can be and are highly biocompatible. We have a 3-electrode setup, which is common for electrochemical measurements for catecholamines, and we use a 2-electrode setup for pH and acetylcholine. So the active part of the sensor is shown in this image, and then they'll be connected to leads developed in different nests of the project. We use a chemical reaction for generating signal. We have an electrode and we increase the potential at the surface of this electrode. As the potential increases, at some point, we have enough energy to steal electrons from these catecholamines, and that produces electrical current. Through measuring this electrical current at that specific potential, we can selectively detect these catecholamines and get information about their concentration. Use a specific waveform to maximize sensitivity and selectivity. Through this project, we've been optimizing the waveform, and the baseline correction, and the surface coding employed in order to enhance selectivity and sensitivity. I'm showing you one plot that we achieved with these electrodes. You can see that the peak for dopamine appears at a different potential versus the peak for serotonin. And that enables us to get selective readout of these catecholamines just through controlling the potential of our electrodes. The peak height specifically, or the peak current value, will correspond to the concentration of these catecholamines, and that's the additional information that we can get in order to quantify the levels. So this plot here shows you the linear correlation between peak current, magnitude, and concentration of dopamine, and we see similar behavior for the rest of the catecholamines. So I told you a little bit about our catecholamine sensing module and how it functions. So basically, we utilize these parallelistically flexible electrodes, but through changing the coatings that we employ in the development of these sensors, we can now selectively detect pH and acetylcholine. The mechanism we use for sensing is slightly different from the perspective that we monitor the surface potential instead of monitoring electrical current. In order to achieve selectivity, we utilize an active sensing membrane. The sensing membrane creates a charge separation at the interface, something we refer to it as electromotive force or electrical potential at the surface. And this electrical potential correlates to the natural log of activity of this biomarkers following the Nernst equation. For pH, we use an oxide coating. For acetylcholine, we use an organic sensing membrane that has a highly stable organic receptor that generates selectivity for acetylcholine specifically. In this part of the project, we modify surface coating, long-term stability, and biocompatibility of these sensors. I'm showing you the response for our acetylcholine sensor. As you see, we are monitoring the EMF value or the potential of these electrodes, and as we change the concentration of acetylcholine in each step, we see a change in the magnitude of the electromotive force. If we plot electromotive force versus log concentration of acetylcholine, we see linear relationship from 10 millimolar to 10 micromolar, and we're optimizing this range to achieve a lower limit of detection. In summary, you can utilize any of these two sensing modules. Current sizes are listed here, but we could also modify the size of these sensors to match the user needs. We don't use any enzymes or antibodies, so they are highly stable in vivo, and we're actually performing a variety of tests in order to ensure long-term stability and biocompatibility for these sensors. Currently, we're modifying the coatings employed in sensor design. Next, we will move for acute studies in order to identify any potential biofouling and solutions to remediate that. By the end of the project period, or June 2025, we will release all the documentation and details of microfabrication and in vivo performance of these electrodes to make sure that users can pick and choose based on their needs and develop the modules customized to their needs. Thank you so much for your attention, and I'd be happy to talk about technical performance and details of the sensor development in the Q&A part.
Hello, everyone. Thanks for sticking around. My name is Alex. I'm a research associate here at CARSS, and I'm going to spend the last part of our webinar briefly discussing how we plan to share what we develop here with the wider research community. So one of the really cool things about the CARSS Center is that everything we develop here is going to be open sourced. This means that everything from CAD models, the actual PCB source files, as well as manufacturing files, any code that we generate, as well as SOPs, testing procedures, test results, and a quality system that we're hoping to put in place around some of our devices will be made open and freely available to the entire research community. Now, when any open source project starts, a lot of thought has to go into what copyright license is going to be used to distribute these files. We're still talking to some lawyers just to make sure we, cross all our T's and dot all our I's, but we expect that the license we use is going to have a couple different conditions. The first two, which are very standard across any open source project, include attribution, meaning if you use data from CARS in any way, you have to cite us essentially. And then a liability release, meaning that if somebody takes CARS data or CARS designs and makes their own device, they are responsible for any of the liability or any of the safety concerns around that device. The third condition that we're going to add to some of these files is going to be a non-commercial clause. This means that anybody who's an academic or who's using these for nonprofit use, you're free to use them however you want. But if you plan to build a device and then sell it or commercialize a device, you need to talk to us first and get a separate individual license. This just ensures that the devices that CARS develops are used responsibly and that there's no legal or liability issues that come up in the future that could threaten the integrity of sort of the CARS project as a whole. Now, as for where these files will actually be stored, some of you might have already seen our website hosted through USC. This is where we're going to have newsletters, updates, other invites to events such as this, as well as links to all of our other resources. The majority of our files are going to be actually stored through GitHub. This is where we'll release the actual source design files. We're also going to host a wiki there that'll have an explanation of like what files go where and include SOPs and best practices. And then we're also going to integrate a forum and discussion platform. So for support, if any of you have any questions or you need to get in contact with us, have any concerns, feel free to post on GitHub. We can send out the direct link to where you can post right after this, and we'll get back to you. Another resource that we're going to use is the Spark portal put on through NIH. That's going to be used to host any benchtop testing results, both the protocols and the results for animal experiments, and then eventually human clinical data. As for our timeline, our first documentation is going to be released here coming up in June. This is going to be initial design files for all of our nests, as well as some initial quality documents for 2 different example indications. We're still working on figuring out exactly what those indications are going to be, but we want to use, between those indications, all devices developed through nests 1 and 3. These are the more, I guess, mature devices. As for the more researchy devices, we're still going to release all of the design files and all the SOPs and testing procedures. We just won't develop a quality system around those. Our final document release is going to include final design files for everything, including any changes that are made between June and our eventual release, as well as manufacturing processes, SOPs, any design of test fixtures or CAD models necessary to test and qualify them, and a full set of quality documents and quality manual for those 2 example indications. We're also going to run a large animal study with the Nest 1 through 3 device to look at safety, as well as 2 small animal studies for the Nest 4 and the Nest 5 devices that'll investigate efficacy in a rat model. Here's a brief timeline, somewhat simplified, but as you can see, the initial document release is coming up. During 2024, we're going to do a lot of prototyping, iteration, benchtop testing, as well as develop those quality manuals I mentioned. We're also going to run the animal studies, and then in Q1 or Q2 2025 will be our final document release. We expect that in around Q2 2025, that's when we can go ahead and use our devices in a first-in-human study. As for our future plans, this is still in process, so if you have any feedback or any advice, please don't hesitate to reach out and let us know. But our plan at the moment is to create a nonprofit center that'll live on after the 3 years of this NIH grant is finished. This nonprofit will sit between our partners, which include, of course, the 3 companies involved in the grant, or the 3 organizations involved in the grant, as well as any other manufacturing or testing partners that we might bring online. And we'll offer any sort of contract services we might put on. We'll sell devices directly to users, and we'll deal with any licensing for commercial companies that might come up. So I mentioned wanting to do first-in-human studies starting in 2025. We are very interested right now in finding collaborators to help develop devices as well as run those studies when we are ready. There's some good funding opportunities available through the NIH Blueprint MedTech project. Those would cover a little bit of device development, where if you or any other researcher you know has an indication that would require some electrode changes or firmware modifications, or anything that's within sort of the desired scope of the CARSS Center, but maybe isn't directly addressed by what we're building at the moment. This funding would help fund that development as well as provide funding for those first-in-human studies. So please get in touch if you're interested in collaborating, if you're interested in working on a grant together. You can email me directly or just email the CARSS Center general email address and I'll get back to you. So that's what I've got. Again, thanks for joining our webinar, and we look forward to talking to you guys more and to have you join us as our project continues.